P block elements, their general properties. The important points in P block. General electronic configuration of P block elements is given by Ns2Np1 to 6. Down the group, the atomic number increases, so the number of shells and subshells increases. So the atomic size also keeps on increasing. Ionization enthalpy is dependent on atomic size. As a result, the atomic radii increases and so the ionization enthalpy decreases. It is easy to remove an electron from a large size atom than a small size atom. Electronegativity decreases down the group as the non-metallic character decreases and metallic character increases. Reducing character of the elements and the hydrides increases down the group, whereas the oxidizing character decreases. Across a period, the atomic size decreases. The reason is the nuclear charge increases but the electrons are entering the same shell. So the nuclear pull increases with the result the atomic size decreases. Non-metallic character increases from left to right and becomes maximum for group 17 elements. The reducing property of the elements decreases across and oxidizing nature increases. Oxygen, phosphorus, sulfur and halogens are very reactive, while the other elements in the P block are less reactive. Coming to anomalous behavior. What do you understand by anomalous behavior? The first member of every group has a different behavior from the rest of the members. This occurs due to small size, high electronegativity, high ionization enthalpy, absence of d orbitals, and in the case of group 15 and 16, they have an ability to form multiple bonds, that is p-pi p-pi multiple bonds or d-pi p-pi multiple bonds. Some typical points in P block elements. The most important one being inert pair effect. These elements show the property of inert pair effect. What do you understand by inert pair effect? As we move down the group, the heavier elements in P block show an oxidation state 2 less than the group oxidation state. This occurs because of the reluctance of the outermost s orbitals in taking part in hybridization or chemical reaction. The s orbitals remain as an inert pair. It's true for heavier elements in group 13, 14, 15 and 16. For example, thallium in group 13 should show +3 oxidation state, but it actually shows only +1, that is 2 less than the group oxidation state. Same is the case with group 14. The heavier element is lead. It shows a stable oxidation state of +2 against the group oxidation state +4. The heavier element in group 15, bismuth, also shows +3 oxidation state instead of +5. Tellurium in group 16 shows an oxidation state of +4 instead of +6. All this happens because of the reluctance of the outermost s orbital in unpairing. Some more important points about P block elements. Nitrogen is a small size atom. It does not have d orbitals. So, it cannot form pentahalides like other elements in the group. The next is regarding oxygen. Oxygen exhibit -2 in its compounds, and whereas the other members show several positive oxidation state including -2. So it can show -2, +2, +4 and +6. Another important point is regarding sulfur dioxide. Sulfur dioxide acts as an oxidizing agent as well as a reducing agent. The bleaching action of chlorine is found to be permanent, whereas that of sulfur dioxide is temporary. This occurs because chlorine's bleaching action is due to auto-oxidation. Next is about interhalogen compounds. Interhalogen compounds are more reactive than their corresponding halogens, as the bonds between these compounds are very reactive or weaker. Group 18 elements are unreactive as they have completed octet except for helium, which is a duplet, and it is found to be stable for K-shell. Some important facts with reasons. Nitrogen is inert in nature. Nitrogen is a gas which is almost inert in nature. Why it happens? That is because of the triple bond that is formed between N2 molecules. Here, you find that the bond dissociation enthalpy of nitrogen is very high. So, to break the bonds, we have to supply a lot of energy, and so it remains as inert. Next is the case with water. Water is a liquid, whereas hydrogen sulfide is a gas. What happens in the case of water? Water is made up of hydrogen and oxygen, and you find that both this hydrogen and oxygen are small size atoms. So, when they are connected together, you find a weak intermolecular force of attraction occurs between them, and that is known as intermolecular hydrogen bonding. That is absent in the case of hydrogen sulfide because sulfur is relatively large in size with low electronegativity. So the only force of attraction between the molecules of hydrogen sulfide is van der Waals force of attraction. These molecules are free to move about as in gas. Coming to hydrides of p block elements. When we compare the hydrides of group 15, you find that bismuthine BiH3 is the strongest reducing agent. As we move down the group, the size of the central atom increases, and so the bond length increases, which reduces the bond strength, and subsequently the bond dissociation enthalpy decreases. That means such compounds can release hydrogen easily, and so they act as better reducing agents. Coming to group 16. If we consider the hydrides, you find that water is the stablest hydride. As we move down the group, we have seen that the size of the central atom increases, bond length increases, bond strength decreases, so bond dissociation enthalpy decreases. That is, thermal stability is found to decrease, and you find that when thermal stability decreases, it is easy to remove hydrogens, or it acts as a better reducing agent. So among the hydrides of group 16, water is the stablest hydride, that is thermally stable, and it is having the highest dissociation enthalpy. Facts about ozone. Ozone is an allotrope of oxygen which is having an angular shape, and it is stabilized by resonance. It is an unstable molecule at normal pressure, that is, it is thermodynamically unstable. When dioxygen molecule absorbs energy, it changes into ozone. It is a pale blue liquid which can be converted to gas as well as a solid. It is toxic in nature, but ozone is a very good oxidizing agent, bleaching agent, and it can also act as a germicidal. Due to these reasons, we find that ozone can be used for purification of water. Now we shall see how to do the quantitative estimation of ozone. Ozone being a gas, the quantitative estimation has to be done indirectly. Ozone is made to treat with potassium iodide, which liberates iodine, which is estimated by treating it with sodium thiosulfate solution using starch indicator in the presence of borate buffer, which maintains the solution at a pH of 9.2. First, the amount of iodine liberated is calculated from the end point of the titration. Knowing the amount of iodine liberated and equating it to the amount of ozone used up, we can exactly find out the amount of ozone can be estimated clearly. Halogens are very good oxidizing agent. Why that halogens become good oxidizing agent? Halogens have strong electron accepting tendency due to high electronegativity, low dissociation enthalpy, and large negative electron gain enthalpy. Next point is fluorine forms only one oxo acid, and that is HOF. Why that fluorine forms only one oxo acid? Due to the small size of fluorine, it does not have d orbitals, and so it can show only one oxidation state, that is -1. Other halogens have d orbitals and can show a variety of positive oxidation state. Due to this reason, fluorine can form only one oxo acid. Halogens are generally colored. Halogens show a variety of colors, and this occurs due to absorption of radiation from the visible region. It results in the excitation of electrons to the higher energy levels. As a result, different halogens absorbs different quanta of radiation, and they display a variety of colors. The first compound of xenon that is identified was synthesized by Niels Bartlett in 1962, and the compound is a complex with the formula Xe positive PTX6 negative.